Now that we understand the concepts of moments and center of mass for both a one-dimensional system and a discrete two-dimensional system, let's think about a continuous two-dimensional system. And we're going to really use the ideas that we developed in the discrete two-dimensional system in order to solve this case. So consider a two-dimensional shape with a uniform density. We'll call the density rho. And we want to imagine this shape lying below the curve f of x above the x-axis from x equals a to x equals b. So let's draw a picture of this. We have some function f of x. We go from x equals a to x equals b. And we're thinking of the area here below the function and above the x-axis. This shape is called a lamina. And we can find the area of this lamina just with a simple integral. To find the area under a curve, we integrate from a to b the function f of x dx. Now, if we imagine a flat plate shaped like this lamina, then the mass is going to be centered at a certain location. Perhaps it would be somewhere around here, perhaps. We can find the center of mass of this lamina by using these formulas. Here's the x value for the center of mass, and here's the y value for the center of mass. We'll talk about where these formulas come from, and then we'll solve several examples using these formulas. And we want to note that the center of mass is also called the centroid of the two-dimensional area. So if we think just of an area rather than an actual two-dimensional lamina, then the area has, instead of a center of mass, it has a centroid. So let's work on developing these formulas. And what we're going to do is take our region and subdivide it into a bunch of small subintervals. And we're going to try to represent the different masses here as point masses. So each of these small subintervals is shaped like a rectangle. And it turns out that a rectangle will have the center of mass at the very center of the length and the width. So if we think of this first rectangle here, the center of mass for that first rectangle is just right in the middle. So for each of these different rectangles, we'll represent the center of mass for the rectangle right in the middle, something like this. The last one has a center of mass about there. So we're effectively taking these different two-dimensional areas and we're representing their center of mass. And so we're converting this from a continuous two-dimensional case to a system of discrete two-dimensional points. We know how to find the center of mass for a two-dimensional discrete system, so we'll use our knowledge of that to convert the center of mass for this continuous region. So now, rather than thinking of all these subdivisions, let's just think of a representative slice of the lamina. So we have a representative slice here. This has some little bit of thickness dx, and it is at a distance of x from the y-axis. We're measuring along the x-axis a distance of x to get to this slice. The height of this slice is the value of the function at x. The height here is simply f of x. And the center of mass is right there in the middle of that rectangle. Now let's think about the x coordinate of the center of mass for this. So we have x bar, which you can write as the moment about the y-axis divided by the mass. And to find the moment about the y-axis, we want to add up all the individual moments. And so we'll find the expression for the moment of this representative slice, and then use an integral to add up all these moments. That will give us the moment about the y-axis. So we want the moment for a representative slice about the y-axis. Well, the moment for this representative slice is the mass of the slice times its distance from the y-axis, which in this case is just x. So just like before when we found the moment for different masses, we just multiplied the mass times the value of the coordinate. Here we multiply mass by the distance from the y-axis, which is simply our value x. Now the mass of the slice is the area times its density. So we can express this as area of the slice times density times this distance x. The area of the slice is the area of this rectangle. So this rectangle has a height of f of x, it has a width of dx, So the area for this slice is f of x times dx. We multiply by rho, and we still have times x. So this expression is the moment of this slice about the y-axis. In order to find the moment of the entire system about the y-axis, we will add up all of the moments. And instead of having a discrete sum, we integrate to add up all of these individual moments. So we could write m sub y as the integral of this expression here. So we integrate rho times x times f of x, integrating with respect to x from a to b. Now we divide by the total mass. The mass is the total area of the entire two-dimensional region times the density. So the mass here we can write as the total area, which we've been calling A, times the density. So A times rho is the mass of the entire lamina. That's the denominator. Now notice that the density cancels. Since we have a constant density, the density here simply cancels. So density doesn't matter in the end. And here is the expression for x bar. Notice that this is exactly the formula that we have over here. So that's the expression for the x value of the center of mass. Let's find the expression for the y value of the center of mass. So the y value is y bar, which is equal to the moment about the x-axis divided by the total mass. Once again, the total mass is simply the area times the density, so we can write that in immediately. And now we want to think of the moment of the entire system about the x-axis. Once again, we're going to focus on an individual slice and find the moment just of this slice about the x-axis. So we want an expression for the moment of the slice, this time about the x-axis. Well, once again, the moment is the mass times the distance. So the mass here, that will be the area times density once again. And the distance, now we're measuring distance to this center of mass of the slice. So the distance will be half of the height, 1/2 times f of x. So the distance here, 1/2 times f of x. We can think of this as one term, m1 times y1. We have the mass times the y value, which is 1/2 of the total height of that rectangle. Once again, mass is area times density. So we can write area times density times 1/2 times the value of the function. The area is once again simply the height of the rectangle, f of x, times its width. So area is once again f of x times dx. So we have f of x dx times rho times 1/2 f of x. Rather a complicated expression. This is the expression for the moment of an individual slice about the x-axis. To find the entire moment about the x-axis for the whole system, we will add up all of these individual moments, and we do that using an integral. So we will integrate this expression here. Notice that we have an f of x times f of x. We can write that as f of x squared. So this integral is the integral from a to b. We have a 1/2 here, and then f of x times itself is f of x squared times dx times rho. Once again, we have a rho in the numerator, a rho in the denominator, and rho is constant, so we can cancel both of those. And this expression here that we get for y bar exactly corresponds to what we were expecting. So to summarize this, if we have a two-dimensional lamina underneath some function f of x from x equals a to x equals b, as long as the density of the lamina is constant, we don't even need to know what the density is, the center of mass for this system is given by x bar and y bar with these formulas here. Let's practice using these formulas in some examples. Take a look at example 3. We want to find the centroid of the region bounded by the x-axis and the function f of x equals 1 minus x squared. Let's go ahead and draw what this looks like. So the function 1 minus x squared is a parabola opening downward. Looks something like this. And we might guess from symmetry that the x component of the centroid will probably be 0. If we think of the mass, it's probably centered around the y-axis, and we'll see that that is indeed the case. So our function, or our region rather, is bounded by the function and the x-axis. So that is the two-dimensional region that we're interested in. First of all, let's figure out what are these x values where the function crosses the x-axis. Well, that happens when 1 minus x squared, that's the height or y value, when the height equals 0. So we have 1 minus x squared equals 0. If we factor, we have x minus 1 times x plus 1 equals 0. So we have two x values, x equals 1 or x equals negative 1. Those are the x values where this function crosses the x-axis. So when we think of the limits of integration from a to b, we will use these values. Now let's write the formulas for x bar and y bar. X bar equals 1 divided by the area times the integral from a to b of x times f of x dx, and y bar is 1 divided by the area times the integral of 1/2 f of x squared dx. Now the area is simply the area under the curve, the integral from -1 to 1 of 1 minus x squared. And if we solve this integral, the antiderivative of 1 is x, the antiderivative of x squared, x cubed divided by 3. We're integrating from -1 to +1, so we first put in 1 minus 1/3, minus -1 minus a -1/3, so plus 1/3. Now if we simplify this, we have a value of 4/3. So the area here, A, is simply 4/3. Now let's focus on the x component of the centroid. We have 1 over A, 1 over 4/3 is 3/4. So 3/4 times the integral from -1 to 1 of x times 1 minus x squared. Now we could take the time to distribute the x, we could solve this integral, but it turns out that this integral has a value of 0. So we have 3/4 times 0. The x component of the centroid is 0. For the y component, we have 1 over a, which is 1 over 4/3, 3/4, times the integral from -1 to 1, 1/2 times the function squared. So we take 1 minus x squared, squared with respect to x. If we were to solve this integral, we would have to expand out the 1 minus x squared quantity squared. And I actually encourage you to pause the video at this point and try, just for practice, expanding out this integral and finding the value by hand. But this should be a straightforward integral to solve, so for sake of time, we'll just use a calculator. And the answer that we get here is 2 over 5, which is equal to 0.4. So this total height here is 1, so we're not quite halfway there. This point right here, this is the centroid of the region. If we were to take a two-dimensional shape, shaped like this region, a lamina, and if we were to put it on this point, it would perfectly balance about this point. That is the centroid of this area.